Here we're given a problem that states the solid cylindrical conductor shown below carries a uniform direct current with a density of 100 amps per meter squared in the positive z direction. We're told to assume a resistivity of 0.1 ohms times meters. So here is a diagram of the conductor. We're given a diameter of 10 centimeters, and we're to assume that this conductor is infinitesimally long and protruding in the z direction. So this problem wants us to solve the power loss in watts per meter length is most nearly which of the four options. So to solve this problem, we have to state our givens. So we're given a current density of 100 amps per meter squared. So if we denote the current density as J equals 100 amps per meter squared. We're also given a resistivity of 0.1 ohms times meters, and we usually denote resistivity as rho. Rho is 0.1 ohms times meters. We're also given a diameter. Diameter is 10 centimeters, so D equals 10 cm. And what are we told to solve for? So the power loss in watts. So P equals question mark. So we also know a formula for power given current, and that's simply P equals I squared R. Well, the problem here is we don't have I and we don't have R, but what we do know is the current density and also the resistivity. And from what we've been taught, you can derive current and resistance from these two quantities. So let's get to it. So I equals current density times area, because amps per meter squared times meter squared gives you amps. So simply to do that, you have 100 amps per meter squared, and the area of a circle is just pi r squared, right? So if we plug that in, pi r squared, and continue to solve, 100 amps per meter squared times pi times 0.05 squared. That gives us I equals 0.7854 amps. Perfect, so we have our current, so now let's solve for our resistance. So a formula that we've been taught before is that resistance equals resistivity times length over area. So what I mentioned before is that this is an infinitesimally long conductor, but that shouldn't matter too much. So we have our resistivity 0.1 ohms times meters times L over A. So A being pi times 0.05 meters squared. And what does this give us? Well, this gives us 12.73 ohms per meter. So now that we have our I and our R, we can plug it back to our power formula, P equals I squared R. And if we plug it in, 0.7854 amps squared times 12.73 ohms per meter. Well, that gives us our power as 7.854 watts. And that's pretty much close to option C. So moving along, we have a problem that states at 80 degrees Fahrenheit, the contact potential for a given p-n junction is 0.026 volts. If the temperature is raised to 180 degrees Fahrenheit, the increase in millivolts in the contact potential will be what? And we have to enter our response in the given blank. So this is a question from solid state electronics and devices. So basically, we are given a formula for the contact potential of a p-n junction, and that formula is V naught equals KT over Q times the natural log of the number of acceptor times the number of donor over the intrinsic carrier squared. So what does this question, or what does this equation rather, tell us? So it tells us that V naught is proportional to the temperature in Kelvin. So we have to do a bit of units conversion here, and we have to convert basically to Kelvin. So we know that degrees Celsius is equal to degrees Fahrenheit minus 32 over 1.8. And then from Celsius to Kelvin, it's just Kelvin equals Celsius plus 273.15. So knowing this information, Kelvin equals degrees Fahrenheit minus 32 over 1.8 plus 273.15. And if we continue at 80 degrees Fahrenheit, if we plug this into the above formula, you get 299.8167 Kelvin. And at 180 degrees Fahrenheit, you get it as 355.3722 Kelvin. So how do we relate this to the formula really? So one way that we can do it is by treating it as a proportion. So it gives us 80 degrees Fahrenheit at 0.026 volts. So we have to find the proportion for 180 degrees Fahrenheit to what voltage. So to do this, we basically have V0 over 0.026 equals 355.3722 Kelvin over 299.8167 Kelvin. And this proportion basically matches because we're matching the 80 degree Fahrenheit voltage to the 80 degree Fahrenheit temperature, and V0 being our unknown, new value at 180 degrees Fahrenheit to the temperature conversion of 80 degrees to, or 180 degrees to Kelvin. So solving this, we get V0 or V naught equals 0.0308. And well, we're not done yet because this is the final temperature at 180 degrees Fahrenheit, and we're told what is the increase? So to find the increase, we have to take the difference of this final value minus our initial value. So our initial value at 80 degrees Fahrenheit was 0.026. So if we take the difference between 0.0308 volts minus 0.026 volts, we get our difference value, or the increase in millivolts, as 0.0048 volts. And converting that to millivolts, that would be 4.8 millivolts increase.